Good evening, good day, good morning. I don't know what time it is. Welcome to our first virtual chemistry class of the semester. Coming at you from the kitchen. So let's begin. We're continuing Unit 4 with kinetics. So last time we saw each other, we were talking about rate laws and how you can express how concentration changes over time for different reactants in a given reaction using experimental data. So if you recall, this is kind of review. We discussed zero order, first order, and second order reactions. So as you can see here, these are general equations and how they generally look. So for zero order reactions, generally it's just rate equals to K times the original concentration raised to the 0 power. As we know, anything raised to the 0 power is equal to 1, so rate really is equal to K. All right, for a first order reaction, rate is equal to K times the concentration of a reactant raised to the first power. And for a second order overall reaction, you have those concentrations raised to a sum of the exponent of 2. All right. So if you look down at these examples here, something important to note is that when you're talking about the order of a reaction, it's the overall order. So the reaction given here, nitrogen monoxide plus ozone going to nitrogen dioxide plus oxygen. As you can see, this is a second order overall reaction because the sum of the exponents is 2. So the reaction is first order with respect to NO, first order with respect to ozone, however, second order overall. And you kind of see a similar thing here going down at the bottom. Now, we don't really discuss third order reactions too much in this class. However, this is a third order reaction because it is second order with respect to NO and first order with respect to H2 with a sum of 3. All right. Now, how does that play in for us here? Today, we're going to be looking at integrated rate laws. And the reason that you might want to integrate a rate law is so that you can see a linear function. You can see a line. So the goal of today is really how do we express integrated rate laws and how do we use these linear functions to determine the order of a reaction. All right. Now, here we go. Let's start with first order stuff. So as we just saw, for a first order reaction, generally the rate is equal to the rate constant times the concentration of a reactant. Integration is a calculus function, so it's the opposite of taking the derivative. It's not something that you're expected to know for this class. So when we're going through these integrals, I kind of just want you to take my word for it, and that's really all you need to know. So when you integrate something raised to the first exponent, basically you get a logarithmic function, and you're going to end up getting ln times this function of a naught. This little 0 is called a naught. So a naught indicates the original amount of whatever you had, divided by the amount left over at time t, equal to the rate constant k times t, where t is always in seconds. All right. So when you rearrange that function, when you divide logarithmic terms, you actually can separate them through subtraction. So you end up getting ln of a naught minus ln a t equals to kt. And if you're familiar with linear functions, this is actually a y equals mx plus b format when you rearrange this. Okay. Continuing with our integrals here, as we saw in the introduction, generally a second order reaction, the rate is equal to K times concentration squared. When you take the integral of something that's squared, you end up getting the reciprocal of that. So it's going to be 1 over a at time t minus 1 over a at time 0 equal to the rate constant k times t. And finally, for a zero order reaction, where you have the rate equals to k times a naught raised to the 0 power, when you take the integral of that, basically you just get things raised to the first power. So it's going to be a at time t minus a at time 0 equals to the negative kt. Important to note that you have negative k for the zero order function. All right. So the AP is not going to ask you to integrate functions. It's not going to ask you to write integrated functions. It's only going to ask you to use those equations to solve for concentrations. Now, those equations are also given on the reference table, so it's not something that you have to memorize. but you do need to know which one is 0, first, and second order. So that's what you're going to be practicing. Okay, let's look at this problem. Sample AP problem here. All right, so at 1,000 degrees Celsius, cyclobutane C4H8 decomposes in a first order reaction with a very high rate constant of 87.1 per second to yield 2 molecules of ethylene. Okay, if the initial concentration is 2 molar, what is the concentration after 0.01 seconds? For part A, and for part B, what fraction of C4H8 has decomposed in this time? All right. So what we first need to know is that this is a first order reaction. All right, now let's go back and look at what the integrated rate law is here. So it's ln A naught minus ln A at time t equal to kt. All right, so just to kind of keep you updated with what I'm doing here, just writing the integrated equation here. Now they also gave us k, the rate constant, equals to 87.1 per second. They also gave us the initial amount, which is A naught, which is 2 molar. And they want us, so just kind of, sorry, this is a little awkward, but A naught is 2 molar. So they want us to solve for A at time t, which is x, and t, they said, is 0.010 seconds. All right, so all we're going to do is just plug right into this equation here and solve. So you just need to know where the ln button on your calculator is. So it's going to be ln times 2 minus ln of x equals to k, which is 87 times t.01. All right, so, bless. You're going to need to rearrange this math and then solve for x. So you're going to need to use the inverse ln function, which is going to be your e button. So let's rearrange this real quick. All right, you're going to subtract ln of 2 minus ln of 2. All right, and then you're going to actually divide that all by -1. So whatever you get here, you're going to do ln x equals 0.87 divided by ln of 2. All right, so again, just trying to kind of consolidate here. 87 times 0.01 is going to be 0.87 divided by ln of 2. All of that we're going to negate. So we're going to divide by this -1 here, this -1 there. And then you're going to be left with ln x equals to this function. Again, to get rid of the ln, you're going to raise this whole function to the e power. So it's going to be e, getting rid of that, e raised to this power. All right. And when you do that in your calculator, you get this, 0.83 molar. Okay. Questions? Let me know. Email me or something. All right, so for part B, what fraction of C4H8 has decomposed in this time? All right, now they're asking us for a fraction of decomposed. So really they want us to look at A naught minus AT over A naught. So they want what fraction has decomposed. So what fraction has gone, I guess. So when you're calculating, A naught is the amount remaining, and that's something that's really important. So when you're talking about the decomposed stuff, that's what has left. So if we look at this, we had 2 molar, and we have decomposed to 0.83. So when you take that difference, you end up getting 1.17 molar, right? And then you can just take the fraction of that divided by 2 molar, you get 0.58. So something like this, the back problem. Again, if you have confusion, let me know. But these problems should really just be plug and chug. All right. Okay. So again, this is really what you need to know for this part. Again, these equations are actually given on the reference table. You just need to know which one is which. So first order is the ln's, second order is the inverse, zero order are the originals. I personally don't really have a good mnemonic for this, so if anyone comes up with a good one, let us know. But as you can see, they all take the form y equals mx plus b. And we've rearranged these here so that you can see that format, where the y's are on the left. The slopes are all the rate constants, if you notice. T is going to be your x, and the b, the y-intercept, are these original amounts here. All right, so let's take a look at what these look like. All right. Now, just in observing here, you should notice that two of these functions have negative slopes, one has a positive slope. So the first order and the zero order reactions both have negative slopes. The second order is the only one with a positive slope. All right. And really, the only thing that you need to be able to do is to recognize the order from a plot. So again, you need to know what the variables are for each of these lines. So again, first order, ln's. Second order, reciprocals. Zero order, are the originals. All right, so you really need to get that down. All right, what they may give you on the AP exam is they may actually give you data, and they may ask you to determine the order based on those data points. So as you can see here, when they give you experimental data, and the important thing to know is that, we use this function, integrated rate laws, generally when they don't give you initial rate or initial concentration data. Remember that the most accurate rates for reactions are ordered at that are determined at that initial moment, because as we know, the rate will slow down as the reaction proceeds, as you run out of reactants and start producing more product. So we use integrated rate laws when you don't have initial reaction data. So if they give you experimental data like this, but it's not, maybe it's not the initial stuff, integrated data can be really useful. So what they've done is they'll give you, the original concentration, the log of that concentration, and the reciprocal. So basically what they're giving you is a plot of the zero order, the first order, and the second order plots. And what they're going to ask you is to determine the rate order based on which plot is going to be linear. All right. Now, generally they won't make you plot this. They'll generally show you the plots here. All right. But what you should be able to determine is which one is linear. All right. And if you can tell from this data, which I doubt that you can, the log function here would be linear. So that would be, we would say that this reaction, whatever it is, would be first order because the ln of the concentration is linear. All right. Cool. So what does this mean? All right, now I'm going to pause here. So I'm going to upload the next kind of bit of this lesson because I ran out of video time. To be continued.